Problem 7 is a geometry problem from the 2019 AIME I and is problem 11. In triangle ABC, the sides have integer lengths and AB equals AC. Circle omega has its center at the incenter of triangle ABC. Let's start drawing that. An X circle of ABC is a circle in the exterior of ABC that is tangent to one side of the triangle and tangent to the extensions of the other two sides. So let's take a look at the X circle first. Tangent to BC. It's going to be tangent to BC, and then it's also going to be tangent to the two extensions of AB and AC. Okay, so that's here. And this is internally tangent to omega, where omega, remember, has its center at the incenter, which is here. We'll call it I, and let's call the X center, the AX center, I sub A. And then by symmetry, we only really need to consider one of the other X circles because they're the same. That's going to look like the point's going to be about here, the center. And we're given that the other two X circles are both externally tangent. Okay, so our circle looks something like this. And we're given that there exists some circle through I that is externally tangent to these two circles. Imagine I drew the other one. And internally tangent to the third bottom circle. Find the minimum possible value of the perimeter of triangle ABC. This does seem like a mouthful, and it really is, but we should be able to solve this with a bit of careful variable assignment and some careful, work. So let's begin with what this tangency condition tells us. One way to leverage the tangency is to relate the tangency points to the two circles' radii, particularly if they are externally tangent. Then the distance between the two centers is simply equal to the sum of the two radii of the circles. Similarly, if we have two circles that are internally tangent, then the distance between their centers is simply the total distance from here to here, which is the larger radius, minus this distance here, the smaller radius, which leaves this distance between the centers. So as we can see, if we let R be the radius of, or let's say R sub omega be the radius of the circle of omega, we can see that this radius can be represented as, the sum of the distance between the centers and the radius of the smaller circle, which we'll call R sub A, And notice that that's equivalent to the IIA equals R omega minus RA, which we would have derived from this fact, using internal tangency to our advantage. Similarly, R omega is also equal to the distance between the centers here, IIC, minus R sub C here, where R sub C is the radius of the CX circle. Notice that, that's equivalent to saying IIC is the sum of the two radii, R omega and RC. The red circle that we drew, really has no purpose other than to relate these lengths, Because, I highly doubt that this circle in particular has special properties. It just gave us this equality here that these two lengths, these two have to be equal. So that I sub A plus R sub A equals IIC minus RC. So if we can find all of the lengths here in terms of, one quantity, we can probably solve for that quantity. The way I'm going to do this is going to seem a bit weird at first, but with some angle chasing, we'll understand why this is. So let's take a look at our diagram here. Imagine our diagram looks like this. Our AX circle looks like this. We need to, and let's suppose that this is the I in center, And then finally, let's say that this is the CX center looks like this, right? So what do we know about these points? Well, first of all, we can say that these points lie on the angle bisectors of A and B, or I guess I should call this I sub B because it's opposite B, or yeah. So this is the BX center, right? And this is the AX center. And similarly, the angle bisector of B passes through I, and it also passes through I sub B. The reason being that the distance from each of these points to the two sides that the angle bisects are equal because they're both equal to the radius of that circle. So you can see that after drawing this, we can actually relate a lot of these. And by drawing these lines, we have also created a bunch of similar triangles. In particular, notice that if we call this angle theta, this angle appears everywhere, right? First of all, it bisects this angle, so we already know that this is also theta. We know that if we draw these, which we also know are angle bisectors because IA is equidistant to all of these sides, AB, AC, and BC, we can see that these are also angle bisectors, and since this is these angles sum to 180 degrees, the remaining two angles are 90 minus theta, right? For that side angle to equal 180, which means that this is theta, and by symmetry, this is 90 minus theta. And we can keep going, right? We can see that if we extend now, notice that the angle bisector of C also passes through I sub B. And since, right, if we look at AC and BC, those two angle bisectors will be the same angle bisector. So IA and IB and I and C are also collinear, right? Because they're just two sides of the angle bisector. So then we can say that this is 90 minus theta, this is 90 minus theta, which gives this is theta, and this entire thing is 90 degrees minus this angle, which is 90 minus theta. So using this, we can actually derive a lot of things, right? In particular, let's just assign some lengths, right? In this case, since we can scale the diagram up and down, let's just call the longer side length, or the side length that is shared at the vertex, let's just call that 1, because this entire diagram is scalable. We'll just need to rescale in order to make all the lengths integers. So let's call that 1, and then we can assign some new points, right? For example, M being, by symmetry, the tangency points of the incircle and the AX circle, which is also the midpoint of BC. We can see that BM is equal to just, well, we can see that cosine of angle B, which is 2 theta, right? Angle ABC is theta plus theta, is equal to BM over 1, which just equals BM. So then BM is equal to cosine 2 theta, which is also equal to MC. Let's give values, say X, and this is the tangency point, Y, and let's say the tangency point up there is Z, between the BX circle and each of the three sides. What can we say about, for example, remember that we're trying to find R sub A, R sub C, IIC, and IIA. Well, okay, let's start with IIA and R sub A. R sub A can be found by looking at the triangle BMI sub A, which is a right triangle because the radius is perpendicular to the tangent line. So looking at this, what can we say about this length? Well, we know that this is R sub A here because it's the radius, and we already know that this is theta, and we know BM is cosine 2 theta. So we can actually just write, well, tangent of theta, which relates to two sides that we know, or the two sides that we want, cosine 2 theta divided by RA. So we can just rewrite RA as cosine 2 theta over tangent theta. This may look messy, and it is, right, it's not very easy to simplify, but we'll see how this can pan out very nicely, because everything's going to be in terms of theta, and hopefully we can find a nice number for theta, or cosine theta, or sine theta, or something similar. Let's do I sub A now. Well, notice that I sub A, well, we can actually write that as an example. IM plus MIA, and IM can be calculated from the triangle BIM with, again, this angle of theta, this being the in radius r, and we can see that this is just IM, right? And then we know that BM is, again, cosine 2 theta. So then we can see that IM over cosine 2 theta is simply cosine theta, or sorry, tangent theta. So IM equals cosine 2 theta times tangent theta. And of course, MIA is just r sub a, right, this length here. So that's just cosine 2 theta over tangent theta. So we can see that IIA is equal to cosine 2 theta times tangent theta plus cosine 2 theta divided by tangent theta, which isn't too bad, right? And then finally, we have IIA. Now we can say, given that we can now move on to IIC and RC. IIC, sorry, I should be calling it IB again and RB, right? Anyway, IIB is this length, which may look weird, but notice how that's just equal to, right, BIB minus BI. Another way to look at it is if we drew this perpendicular from I to IB, this radius IBX, right, we would, because IBX is perpendicular to that line BC, we would have a right triangle where this length here is equal to this length here, MX. So actually, one way to find that is, well, this angle must be theta by parallel lines, right, from this angle. So we can see that IIB is just equal to, well, IIB is the hypotenuse of this, and you see that, for example, this length, which is just equal to MX. So MX over IIB, right, since these two lengths are equal, is just equal to cosine theta. So if we can find MX, then we're done, right? We can find IIB as well. In order to do that, we're going to find, we know that IIB, well, we need to figure out what MX is, right? So MX, we can do a little bit of angle chasing, right? And use equal lengths. In particular, lengths of tangent lines to a circle are always equal. So for example, we can write the relation, notice that, for example, MX is equal to, or CX equals CY, because there are two tangent lines from C. And then similarly, AY equals AZ, because there are tangents to this X circle through A. And then we also know that BX equals BZ, right? If we consider this situation, it turns out that we can use these three relations and basically write CX or MX, CX and MX in terms of the three side lengths. And I'll present this here without proof, but we can say that we actually get that MX is equal to 1, which is a really nice fact. And that also tells us that CX is equal to 1 minus MC, which is just cosine 2 theta. Right, so actually we have that IIB is just MX over cosine theta, which is 1 over cosine theta. And then finally, in order to find I sub B, we can use this triangle here, which I'll just use a new color to shade in. Look at this triangle here. This has an angle of theta at the I sub B and has a length CX equals 1 minus cosine 2 theta. So actually this gives us that IBX, which is just R sub B, or IBX, R sub B is equal to, well, we can write that as cx over tangent theta, right? Because tangent theta is cx over r sub b. So therefore, we get that this is just equal to cx is just 1 minus cosine 2 theta divided by tangent theta. Okay. So now notice the relationship between IA and the relationship between r sub a here and r sub b. Notice that they add up to 1 over tangent theta really nicely. So this gives us a way to proceed. So I don't have very much space here, so I'm just gonna continue on the previous page. But we can see that we can substitute the 4 values here. I sub a is just equal to cosine 2 theta times tangent theta plus cosine 2 theta over tangent theta plus r sub a, which is equal to cosine 2 theta over tangent theta, is equal to IIB, which is 1 minus, or IIB is over here, 1 over cosine theta. And then we subtract that all by 1 minus cosine 2 theta over tangent theta. If we bring this to this side, we can see that cosine 2 theta over tangent theta and this, right, this is minus, so it'll add up. So we get a total of 1 over tangent theta here. So we get cosine 2 theta tangent theta plus 1 over tangent theta plus cosine 2 theta over tangent theta equals 1 over cosine theta. And at this point we can say, all right, we know that we can make simplifications here. So for example, notice that we can, first of all, separate the tangents to sine and cosine, right? Cosine 2 theta times sine over cosine plus cosine over sine plus cosine 2 theta times cosine over sine equals 1 over cosine theta. At this point, we can multiply through by cosine theta times sine theta. We're going to get a lot of terms like with cosine squared and sine squared and so on. And it turns out that we can write a single equation in terms of sine theta, and that equation happens to be quadratic. I'm going to write it here, but we can go through that process to get sine theta. Remember, theta is this angle here. Sine theta equals 2/3. And we can see that if AB was 1, then this length is cosine 2 theta. Recall that cosine 2 theta is 1 minus sine squared theta, 2 sine squared theta. In this case, sine squared theta is 4/9, so 1 minus 2 times that is just 8/9. So it's 1 minus 8/9 or 1/9. So that we have basically this triangle here. With sine lengths of 1, 1, and 1/9 and 1/9 or 2/9. We can see that the smallest such triangle that satisfies this with integer lengths is that multiplied by 9. So we have 9, 9, and the bottom is 2/9 becomes 2. So our final answer is 20, right? The perimeter becomes 20.